Can you start your presentation now?
Okay, yes, I can. Okay. Wait a minute.
Thank you. Thank you.
Okay, let's see the PPT.
Yeah, we see your presentation.
Okay. Uh, so, okay, is everything fine? So I can start the PPT.
Yes, everything is fine.
Okay, the topic is the land-water energy nexus in agricultural management for greenhouse gas mitigation. It's a paper from my group. And the four parts: an introduction, methodology, results, and also some conclusions. And here, agriculture uses almost 40% of the Earth's ice-free land surface, and also, the highest water consumption for almost, the irrigation accounts for almost 90% of the water consumption worldwide, and also 15 to 20% of the global energy use. And also, agriculture is the largest anthropogenic, nitrous oxide emission source in the world. And also, we know that paddy field, rice cropping, is one of the largest sources of methane emission. We know that agriculture contributes almost 20 to 35 of the global anthropogenic greenhouse gas emissions. And also, let's see, towards 2050, in the next few decades, global population is going to increase by a third, and also global income triples during the next 30 years. So the demand for cropland use will increase by 67%, exceed, the food-related planetary boundary for cropland use by 70%. And also the demand for blue water use will increase by 65%. Also, um, uh, um, and also exceeded, the food-related planetary, boundary for blue water use by 50%. And also, of course, the greenhouse gas emissions will increase by almost 87%. So, according to the work published in Science, by Clark, in this year, current trends in global food system emissions would preclude, achieving the 1.5 or 2 centigrade climate change targets. So how to ensure the food security from an increasing population while reducing GHG emissions? So here we want to use the the nexus. We want to analyze the resource base, the land, and also the water, and also the energy, the nexus, and also we want to get the output of the food, and also its food production, and also its environmental impacts, and then we achieve the goal of sustainable agriculture and get the win-win strategy. So here we can see the advantages of nexus approaches. Here we get the picture from Jianguo Liu from the US. And we can see that the nexus approaches can uncover, the synergies and the co-benefits, and also detect the harmful trade-offs, and unveiling, the unexpected consequences, and also enhance the integrated planning, decision making, and also the related management. And here we'll focus on the land-water-energy nexus in crop production, not all the agricultural activities like the livestock or something, just on the cropping system. So we know that the interaction and the use efficiency of land, water, and energy will affect the GHG emissions and the crop production. Here's the nexus framework for the whole cropping system. For example, the land management affects water use through cropping structure and also water supply. will affect the cropping pattern choices and the yields. And at the same time, we can see that the cropping structure and the soil nutrient input will affect the energy use, and the energy supply will affect the crop yields. And for the water and energy, you can see the irrigation, water pumping, and the convey will need energy or something like that. So we can see, the major sources of greenhouse gas emissions, like the application of nitrogen fertilizers. They will actually emit, they will emit, the nitrous oxide, and also the production of rice in paddy fields will emit, methane, and also the combustion of fossil fuels in irrigation and other agricultural activities will emit CO2. Here we use the nexus management in crop production will help improve the resource use efficiency and also identify the major driving forces of GHG emissions, and also we can explore the context specific solutions for sustainable agriculture. So here our study wants to establish a framework for land, water, energy nexus in context of crop greenhouse gas emissions, and clarify the impacts of the land, water, energy use on the crop production, and also assess the GHG mitigation potential of improved nexus management by scenario analysis. So here is the methodology. We can see the study area. We choose the Sanjiang Plain, located in the northeast China. It is one of China's major grain producing areas. And also irrigated rice is the dominant cropping system. There are some problems, of course, like the groundwater resource over exploitation, because they use the groundwater, and also the groundwater level, water level is lower and lower, and also they need more energy consumption for water pumping, something like that. So here we'll make an inventory analysis focusing on the land use. Now, the irrigated rice and the rain-fed crops, and also the water use like the green water and the blue water, and also the energy use like the direct energy and also the indirect energy. And then we calculate, the greenhouse gas emissions, including nitrous oxide and also methane and the CO2. So here we use the integrated framework of LCA, life cycle analysis assessment. And this is the framework. We can see, for the land, we'll, describe the land cover like a crop mix and soil areas. And also we consider, the different types of soil crop nutrient management, like, the nitrogen application rate and crop yield, and also fertilization fertilizing practice, and considering the soil properties. And then we get the ammonia emissions and the leaching and the runoff and the fertilizer input or something. Then we can calculate the emissions. And then regarding the water, we will collect the data of precipitation, and also we calculate the crop water requirements, and also the net irrigation requirement. And then we use the water use efficiencies, and we can calculate the gross irrigation requirements and some methods. So we can then estimate the water source consumption and also the groundwater depth. And then regarding the energy, we have the direct energy use, like energy used for irrigation for the agriculture cropping system, and the on-site energy use, and also some indirect energy use, like using LCA will trace back to the upstream of the, for example, the fertilizer production chain, and we can calculate the indirect energy use, and those are some other chemicals and the machines. So we include both cropping structure and the soil nutrient management into land management. And for the water management, we identify the water source, groundwater depth, and the irrigation water use efficiency as the impact factors. And also regarding the energy management, we'll use the detailed irrigation energy use and also the upstream energy use. Here's the calculation. We can see the Heilongjiang, we use the GIS, we get the data, land use, and also the water use, like the green water, the precipitation, and then the blue water, something, and also the energy use. We can see the on-site, energy use for irrigation, and also the upstream, like we use the input-output table. And also there's some data from the SEAS, database, so we get the comprehensive energy use. So then we get the greenhouse gas emissions is like the methane, emission from paddy fields, and also NO2, emission from the nitrogen fertilizer application, and also some other energy uses. And then we set up, the scenario analysis for the mitigation potential. We have 5 scenarios. Like the first is, the baseline business usual from 2015 to 2020, and then S1. You can see this is the scenario of change of cropping structure. The half of the rice area converted to wheat cropland, because the rice area, they need much more water. So if what will happen after half of the rice area converted to the wheat cropland, and also the decreased S2 decreased fertilizer application. So it's a scenario of zero growth in chemical fertilizer use by 2020. And S3, this is improved water use, like the water use efficiency increased by 3% or something like that. And also S4, decreased the energy intensity, like energy intensity decreased by 50%. And then S5 is a combination of S2, S3, and S4. So we want to cover the potential policy change, like the cropping structure adjustment, and also the possible technology improvement for the agriculture in China. So this is the results and the discussion. We can see the stakeholder of land, water, and energy use for crop production in the Xinjiang Plain. You can see that in 2015, almost 3 million hectare of arable land and the fresh water and the fossil fuels were used for grain crop production on the Xinjiang Plain. And also rice fields produced almost 29% of the total crop protein, occupy 34% of the total cropland. So here we don't use the the yields of the total the cropping system. We use the crop protein, so it's more easy to compare all of the results. This is the greenhouse gas emissions from crop production in 2015. You can see that the rice and the non-rice, the percentages, for example, the 45% from the non-rice production and 55% for the rice system. And also most of them, for example, for CO2 and 17 for emission, and also nexus 17, and also for the energy use, indirect greenhouse gas 48, and also almost the similar, direct greenhouse gas emissions of 52. So this is the spatial distribution of the greenhouse gas emissions. You can see most of the greenhouse gas emissions are focused on the central part. You can see the mainly wetlands. 2 decades ago, but now there's been have been transferred to the paddy fields. Then the greenhouse gas emissions changed, and also we can see the right part. We can see the greenhouse gas emission intensity and the protein productivity. You can see that, and we can see we want to get a win-win strategy with high protein productivity and a low greenhouse gas intensity. And we can see these areas have relatively small proportions of arable land devoted to rice production, and also areas with low protein productivities and high greenhouse gas intensity have a relatively large proportions of arable land devoted to rice production. And this is the impact of a cropping structure on greenhouse emissions. And we can see, the left, we can see the protein productivity and the greenhouse gas intensity. The rice, has the highest greenhouse gas intensity, the highest, but relatively, low protein productivity. And reasons that the decomposition and the associated methane flux caused by paddy flooding, and also the water and energy consumption per unit area of rice production is higher than the other crops, because you need the water pumping and also the irrigation. So the paddy fields, they consume more energy and water, and also emit much more greenhouse gas emission. And also the impacts of land, water, and energy use on greenhouse gas emissions, like the land nutrient use, like for example, the fertilizer application is the smallest contributor, only 7% of the total emissions. But the upstream fertilizer production chain, because we use the LCA method, so we can see that such kind of indirect emissions contribute almost 18 to 31% of the total greenhouse gas emission. And for the water use, we can see groundwater irrigation consumes much more energy than the surface water irrigation. Because we need a pumping system. And also the lower groundwater level results in greater use of energy for pumping water. And also the lower irrigation water use efficiency results in more water extraction. And of course, for the energy use, indirect energy use contributes much more of the total energy use, and the low energy efficiency, and also energy consumption structure based on fossil fuels, can result in higher CO2 emissions. This is the potential of the greenhouse gas mitigation in 2020 by scenario analysis. So we can see that for the five scenarios, we can see the change of cropping structure will cause a decrease by almost 18.8% compared to the business as usual. And as two, you can see the fertilizer application decreased by 8.6%, and for the improved water use efficiency and decreased by 8%, and the energy intensity decrease will also compared results in 11%, and also the combination, of course, 24% almost compared to the baseline scenario. And also we can see other cases, compared to the other cases, showing the benefits of cropping structure adjustment. In India, for example, it is estimated that reducing rice production by % and increase some other cereals for compensation could mitigate the emissions by 70%. It is a paper published in 2016. So, and also in North China, we are adopting the paddy land to dry land program initiated in 2001. So we want to protect the quality and the quantity of the downstream water, for example, in Beijing. So we transfer the paddy land to the dry land. But there are some problems, of course, and something like the environmental risk will be transferred. For example, in Sanjiang, Sanjiang Plain, if we transfer the paddy land to dry land, we can see that the high clay content of the poor drainage of the soil are unsuitable for dry land crops, and also will cause increase in temperature benefits, the rice production, and also the planting rice brings higher economic benefits. Fortunately, the greenhouse gas mitigation effect of integrated technology improvements would be larger than that achieved through cropping structure adjustment. So it's a trade-off. Let's see. Oh, there are four kinds of, in North China, a major like, the crop system like the rice and the corn, soybean, and the wheat. You can see the net benefits. So the policy implications, why we use, the nexus methods, we want to find out we want to promote the synergies and avoid trade-offs in, the multi-resource management, like, for example, trade-off, for example, the water-saving technologies usually consume higher energy, but we also have synergy, like the change groundwater irrigation to the surface water irrigation could protect the local groundwater and also decrease the energy use. And also the indirect energy use should be considered, in developing, the carbon abatement policies, especially those chemical fertilizers. So conclusions. So here we propose a land-water energy nexus based on the greenhouse gas emissions, and also we found that the rice yields produced 29% of the total crop protein, while emitted 54% of the total cropping greenhouse gas emissions, and also the cropping structural adjustment. So the conversion of half of the paddy yields into the dry land crops will decrease the greenhouse gas emissions by 18.8%, and so improve the resource efficiency, including the nutrient management, groundwater protection, and the water saving irrigation technology, and some energy technology could reduce the greenhouse gas by almost 24%. Okay, thank you. My talk is.
Thank you very much for your interesting presentation. And